Hello, my name is Andrew. Today, I want to talk about the latest support tools we have added to the Eclipse Lyo, which we hope will further facilitate the development of OSLC adapters and toolchains. Through its SDK, Eclipse Lyo already provides necessary features to make the job of an adapter developer easier. We build on those features and apply a model-based approach to increase the level of abstraction when developing OSLC adapters. What is Eclipse Lyo? Lyo is an Eclipse project aimed at helping the community adopt OSLC specifications and build OSLC-compliant tools. The core feature of Lyo is the software development kit, OSLC for J, that helps accelerating the development of OSLC servers and clients. Lyo also contains sample code, tutorials, documentation, as well as a set of reference implementations of OSLC specifications. Lyo is particularly helpful during the implementation phase of an OSLC adapter. But when building a toolchain, much work is needed before one even gets to the stage of realizing a single adapter. So, we want to complement Lyo to support the architect in defining the overall toolchain architecture. From our experiences, we found that people tend to use a UML tool or PowerPoint to define their information model, which is a specification of the resources they want their tools to share. Of course, none of these models reflect the true semantics behind an OSLC-based information model. Can we instead provide an OSLC-specific language to allow the architect to define an OSLC-compliant information model? Also, how can we ensure that an adapter implementation still meets the architecture specified in PowerPoint or UML, particularly when the architecture is changing over time? Finally, we found that quite a lot of knowledge of the OSLC standard, as well as its many technologies, is needed just to get started developing an OSLC adapter. Can we abstract away some of these technologies and standards? After all, the OSLC protocol defines a specific pattern for tool interfaces. So, how does Lyo Toolchain Designer help? We want to move the focus from a single adapter implementation to the toolchain architecture and specification. We also want to increase the level of abstraction by taking a model-based approach, both when developing OSLC adapters, but also when defining the whole architecture. We want to provide graphical representations of the toolchain, which are rich and accurate enough to generate the code from. We provide the toolchain architecture with an Eclipse plugin to graphically model a whole toolchain according to the OSLC standard, as well as to generate the code for each adapter to ensure OSLC compliance. The language is structured into a set of views, in which each view focuses on a specific aspect of a toolchain development. We identified the following three views. On the left, you can see the information modeling view, for the specification of the OSLC resources to be shared across the toolchain according to the OSLC standard. In the top right corner, you can see the toolchain architecture view, for the specification of the toolchain architecture. This specifies the distribution of resources across the tools in the toolchains, both in terms of the providers as well as consumers of resources. In the bottom right corner, you can see the adapter architecture view, for the detailed design and implementation of each tool interface according to the OSLC standard. By providing this integrated set of views, we ensure that adapter implementations are compliant with the architecture. I will here demonstrate how to use the Toolchain Designer to develop a small toolchain for Jira. Jira adapter will partially implement the change management specification. To make the example slightly more complicated, Jira will retrieve information about its users from another tool, a user directory tool. To make adapter development even easier, we introduce another component, Lyo Store. Lyo Store allows adapter developers to store and retrieve resources from the triple store using simple ORM-like operations. Once the tool artifacts are stored in the triple store, Lyo Store can be used to respond to client GET requests without any additional tool-specific code. Let's take a closer look at the detailed architecture of the toolchain. I will demonstrate this with a simple request flow. Whenever the end user performs an operation on Jira issues, a Jira webhook triggers a notification that is then captured by the Jira adapter. Jira adapter then creates a change request that corresponds to this changed issue. In doing so, Jira adapter will query the user directory adapter to link to the appropriate creator of that issue. Finally, the adapter persists the change request resource in a local triple store. Now, when the OSLC client makes a GET request or performs a query on a change request, the Jira adapter can simply retrieve the change request from its triple store. It's worth noting here that whenever a request comes for a change request, Jira adapter only fetches them from the triple store using Lyo Store library and no communication happens between the adapter and the original tool. We'll now switch to Eclipse to demonstrate how the Jira toolchain is developed. First, let's create a modeling project. Now let's create the toolchain model. And here you can see the two views of the toolchain architecture and the resource specification. So let's start with the specification diagram. I will start by defining 4 domains. I will set their names and other properties. Now I will define some literal properties and configure their shape according to the OSLC standard. Note that I'm defining the standard for and determined domains here. Of course, it's possible to import external definitions to your model. Now I want to add the person resource to the for domain. Next, I will define the reference property creator on the CM domain with the range person. Once the properties are defined, I can allocate them to the resources. Of course, we can allocate properties from any domain to a particular resource. Note that when I add a reference property, it will be shown on the diagram as an arrow. So now that the specification diagram is finished, we can define the toolchain. For that, let's open the toolchain diagram and define 2 interfaces. For each interface, we define the path of the resulting adapter where the generated code will be output. Now that we have defined our toolchain, let's define the adapter interface of the Jira adapter. To do that, we need to double-click on its element on the diagram. This will create a new adapter interface diagram. So here you can see a default adapter architecture that includes a service provider catalog, 1 service provider kind, and 1 service with a basic capability. First, let's add the change request resource that this adapter will manage. We will also define a query capability on the change request resource. Additionally, let's add another resource under a separate service for managing the projects. Of course, this structure reflects the OSLC core specification. You can also define creation factories and delegated UIs for creation and selection. Now we have a finished architecture for the Jira adapter. We can now move on to the user adapter. We'll add the person resource to the basic capability of the user adapter and define the query capability on it. Now, as you remember from the request flow of the toolchain, Jira adapter makes a request to the user adapter to match the person from the change request. Let's reflect it in the model as well. We'll open Jira adapter interface and add a consumed resource and select person. This will cause the generator to produce a client in a generated adapter. Now that the adapter has been fully modeled, we can generate the whole toolchain. Before we can generate the toolchain though, we need to make sure that the OSLC project skeletons for both adapters are in place. Instructions for setting up any OSLC adapter can be found at the Lyo project wiki. Now that the generation has finished, let's do a walk through the generated adapter code before finishing the implementation and running it. We'll take the Jira adapter as an example. Adapter contains 2 main packages, resources and services. Under the resources package, you can see that we generate Java classes for each of the OSLC resources we have defined in the model. These Java classes will have the OSLC annotations that are required for OSLC-for-J library to perform marshalling and unmarshalling of the OSLC resource instances to and from their RDF representation. These annotated classes, therefore, represent the domain specification. Under the services package, you'll see JAX-RS classes that correspond to the OSLC services that we have defined. Again, these classes and methods reflect the definitions in the model. For example, here you can see the definition of the query capability for the change request that we have defined, and all this code is ready to run. You will see some placeholder blocks where the developer can write custom code. The code added within these blocks will always be preserved when the adapters are regenerated to reflect the change in the model. Of course, we generate JAX-RS services for the service provider catalog and service provider kinds, so that the client can navigate the adapter according to the OSLC standard. Another important class is the manager class. It contains all the methods that the developer needs to implement to get a fully functional adapter. For example, in the getChangeRequest method, the developer should return an instance of the changeRequest resource, given the service provider ID and the changeRequest ID. We implemented it to simply retrieve the corresponding resource from the triple store, using the Lyo store library using 2 lines of code. We have implemented the rest of the adapter by using Lyo store library in the similar way, and by adding a custom JAX-RS interface to handle the incoming Jira webhook notifications. We'll now look at how the finished toolchain works, by running it in the debugger and looking at how the execution happens behind the scenes. So now I have switched to the IntelliJ IDEA to run the demo. This is because generated projects contain no Eclipse-specific dependencies. Well, that, and because I like IntelliJ's IDEA debugger much more. Now I'll set the breakpoints in both adapters for each step of the request flow and run them in the debugger. Let's begin with the user adapter, where I will set the breakpoint on the method responsible for the basic capability on the person resource. All such methods are grouped together in the adapter manager class for your convenience, but the rest of the code can also be customized inside the protected comment blocks shown before. Now that we have set the breakpoint, user adapter can be started in the debugger. In the meanwhile, let's switch to the Jira adapter. First, we want to set the breakpoints on the handler method in the Jira webhook service. This class is not generated, and you can choose any method of integrating the adapter with the actual tool. The first breakpoint will get triggered when the hook notification will be received from Jira. Also, I set the breakpoint right before the change request resource is persisted in the triple store. While the change request is being constructed, the person resource will be retrieved from the user adapter via the generated client. While the change request is being constructed, the person resource will be retrieved from the user adapter via the generated client. Breakpoint in the fetchPerson method will get triggered right before the request. For the client request flow, we'll set 2 breakpoints in the adapter manager, in the methods handling the query capability and basic capability on the change request resource respectively. Now we can run Jira adapter in the debugger as well. Now that the user adapter as well as the Jira adapter have started, we can navigate to Jira and create a test issue. Now we are in the method handling the incoming webhook, and we are constructing the corresponding change request. Here we make a request to the user adapter via the generated client to retrieve the corresponding person resource. And if we run this, we'll land in the debugger of the person adapter in the method that handles the basic capability on the person resource. If we let it run, back in the Jira adapter, we get the person resource as expected, and the complete change request resource is constructed. Finally, here we are persisting the change request in the triple store using the Lyo store library. Now we can request the change resource from the Jira adapter itself. We'll do this through a web interface first. We navigate to the service provider catalog, then through the statically defined service provider to the query capability for the change request. You can see the newly created issue that links to the person resource, which we can also navigate to. Now let's do the same through the Insomnia REST client. Once we do the request, you can see that we have landed in the generated method that handles basic capability requests for an RDF representation of the change request resource. Now we get the RDF representation of the same resource as expected. The generated adapter handles content negotiation automatically. You can develop a similar toolchain consisting of 2 adapters yourself by taking the online workshop available in the Lyo wiki via the link you see on the screen. This concludes our demo. I would like to thank you for attention and point you to 2 links you see on the screen. First link will take you to the Lyo website, where you can find documentation and link to the full workshop. You're welcome to contact me or Jad using our emails that you can see on the screen. Thank you.